Welcome to chemistry episode number 6, radioactivity. So to understand radioactivity, you first need to understand isotopes over here. So isotopes are the different forms of atoms of a certain element with differing numbers of neutrons. So if you could refer back to chemistry episode number 1, the structure of an atom, neutrons, we haven't talked much about neutrons, but neutrons are important for radioactivity. So the different isotopes of an element are the differing versions of an element with differing amounts of neutrons. That's what makes them different, right? For example, one isotope of helium is helium 4. So helium 4 has 2 neutrons, but there's also helium 3, right? So helium 3 has 2 neutrons. Helium 3 has 1 neutron. So the isotopes are basically just the different forms of an element with different amounts of neutrons. That's what makes them different. Now, to notate an isotope, you have the element, and then you have the mass, the atomic mass of the element, of the isotope. So here we have helium 4. So I represented the protons with a plus sign and the neutrons with no sign, right? So helium 4. So the mass, if you could refer back to the periodic table, episode number 3, the atomic mass of atom is the number of protons plus the number of neutrons. So if you could count up here, there's 2 protons and 2 neutrons. So the atomic mass is 4. So this is why this is the helium 4 isotope. Now you could figure out how many neutrons an isotope has if you just knew the number of protons of the element, right? So helium, if you knew that helium had 2 protons, subtracted from this number, you'll get 2 neutrons. So helium 4 contains 2 protons and 2 neutrons. Now, radioactive is a term used to describe unstable isotopes of an element. So now all isotopes aren't stable, meaning that they don't exist, they don't want to exist basically. So they're eventually going to decay, right? Not all isotopes are stable and they'll eventually decay into a more stable isotope, right? And this might not happen immediately, right? It might decay into another unstable isotope, and this is called a decay chain, right? It'll keep decaying until it gets to a stable isotope. Now, these are the different types of decaying, right? First, there's beta decay. Beta decay is when an electron is emitted from a neutron and so it becomes a proton. Remember, neutrons have a neutral charge. So if you take a negative charge away from it, it's going to become positive. Now this is beta minus decay. Beta minus decay is when a neutron becomes a proton. Beta plus decay is when a proton becomes a neutron. This is an example of beta minus decay. So H3 hydrogen 3 isotope, helium 3 helium isotope. So H3 isotope of hydrogen, one neutron becomes a proton and it releases an electron and becomes a helium 3 isotope, which is stable. Next, there was alpha decay. So here we have beryllium 8 isotope, the beryllium 8 isotope, and the helium 4 isotope. Now, beta decay is when a helium 4 particle is released. This is called an alpha particle, right? An alpha particle or a helium 4 isotope is released for the atom to become more stable. In this case, 2 alpha particles are released because when beryllium 8 releases the alpha particle, it becomes another alpha particle, helium 4. But this is obviously not the case with all atoms. I just decided to pick an easier one to draw. More complex atoms, it would emit an alpha particle and become something else than an alpha particle, right? It would become some other complex atom, right? The final form of decay that we're going to be extensively talking about here is gamma decay. So gamma decay is unlike the rest. So as you can see here, this is a hydrogen 1 isotope, hydrogen 1 isotope. Now, as you can see, there's no change, right? It's just a hydrogen isotope, and then it becomes another hydrogen isotope. The same hydrogen isotope, I should say. So yeah, H1 becomes H1. That's because gamma decay, it releases gamma rays, right? When a atom is excited, meaning it has too much energy, it releases that energy in the form of gamma rays over here, right? So the number of protons, neutrons, and electrons stays the same. It's just it releases that energy. Now we're going to talk about a few other forms of decay briefly. So there's proton decay. So an atom just emits a proton. There's neutron decay. An atom emits a neutron. And finally, for this episode, we're going to be talking about half-lives. So half-lives of an isotope it's the amount of time that takes for half of the atoms of that isotope that exists in the universe to decay, right? And this doesn't just have to be for in the universe. It's just any quantity of those isotopes, right? If you have like a kilogram of uranium, right, it would have the same half-life as all of the uranium in the universe, right? The half of the atoms in that kilogram of uranium would decay at the same time, or it's supposed to decay at around the same time as the half the atoms of uranium would decay in the universe, right? So we can't just say we can't define full lives because decay is kind of random, so you can't really put a time on when all the atoms of a given isotope would have decayed, because that's hard, because one atom could live for way longer than all the other ones do. So we just say half-lives to describe the how radioactive a substance is. And I think that's going to be it for chemistry episode number 6, radioactivity. The key things to take away: isotopes, so they're the different forms of an element with different amounts of neutrons, what makes them different. So how to denote an isotope: so this number is just the atomic mass. Beta decay, so beta plus decay would be a proton turning into a neutron. Beta minus decay is a neutron turning into a proton. Alpha decay, so it lets out an alpha particle, which is just a helium-4 isotope. And gamma decay, when an atom is excited, so it releases a gamma ray. And finally, half-lives, which we just talked about. It's how long a half of the atoms of a given isotope will decay. And I'll see you next time in chemistry episode number 7, nuclear fusion and nuclear fission, which has much to do with this episode.